Hello, this is Mrs. Black again. Some of the students were having issues with this problem similar to this, so find the value for the tension in the diagonal rope and the angle theta. So this is the angle theta, here's the diagonal rope. Alright, here is a spring scale that's pulling to the left at 40 newtons, so that's a tension. And then, of course, you have the gravitational force on this box, which will be 3 kilograms times 10 newtons per kilogram, and that's downward. And then the tension here is diagonal. Of course, you know that the ceiling never touches this box, so it doesn't provide a force at all. Alright, therefore, the correct drawing would be like this, and that would be the force tension on the box from the rope, and then this way would be the force tension on the box from the spring scale. Alright, and then straight down would be the gravitational force on the box from the earth. Alright, and then this would be the angle theta. Alright, so we know that gravitational force equals 10 newtons per kilogram times 3 kilograms. Kilograms divide out, so gravitational force is 30 newtons. Alright, so now we know that this is 30 newtons, and we know that this is 40 newtons. Okay, so we should be able to pretty easily figure out what this force is right here. We can just use Pythagorean theorem. Alright, I'm going to divide both of these by 10 because they both get divided by 10 pretty easily. So this will be 4 and 3. Oh wait, if this is 4 and 3, then this is a 3, 4, 5 triangle. So if this is 30 and this is 40, that must be 50. So 50 newtons. Let's see if that works out. If I do F tension equals the square root of 30 squared plus 40 squared, and I calculate that out, yeah, that's 900 plus 1600. That's a square root of 900 and 1600 is 2500. So the square root of 2500 is, whoops, that's 50. I know that kind of look like 60. That's 50 newtons. Alright, so that's correct. So then it is a 3, 4, 5 triangle. If it's a 3, 4, 5 triangle, this angle here is opposite the 4. So the angle opposite the 4 in a 3, 4, 5 is 53. So the angle, 53 degrees. It's that easy. Okay, here's another ramp problem. This person's being pulled up a frictionless slope at a constant velocity by this. So the person's in contact with the slope. The slope's not providing any friction, but it is providing a normal force up. This rope is providing tension that way, and of course there's gravitational force straight down. So the diagram would look like this. Normal force on the person from the slope, tension on the person from the rope. That's a P there. And then straight down, gravitational force on the person from the earth. Alright, pretty simple. Okay, here are two more things. Here's a capital T held in place by this rope and that rope, so you have tension, tension. And of course there's the gravitational force on the capital letter T. That's like a big sign, just a big T. And then here's like a Christmas star held in place by two ropes. And again, remember the ceiling is not in contact with either one. Alright, so I can put the diagram for the T over here. So we have force, tension, and another force, tension, and then gravitational. Now this is on the T by the earth, and let's just say both of those are on T by ropes. Alright, and then the star, you have force, tension on star by rope. You have force, tension on the star by the rope, and then straight down, gravitational force on star by rope.